All right, thank you very much for the opportunity to speak here in front of you today. I'm going to tell you about the work of my PhD advisor, Larry Spanish, who is here, and our postdoc, here at Maria. This is a paper from September of last year, and I was debating whether to talk on beautiful old work or work that I'm very excited about now, and I decided to talk on this published result. The title is pretty telling. Some of you who are more on the computability side might have some ideas that I'm going to tell you about. Let me remind you that string theory in these cases has been a topic that physicists and mathematicians alike have studied for the last 30 years or something like that. And to me, it's particularly beautiful that when you consider quantizing a string and the ramifications that come out of that, string theory naturally gives rise to the sorts of ingredients that we see in nature. In particular, we want a theory of quantum gravity so that general relativity can fit into quantum physics. We want gauge theories with realistic matter, so by this I'm asking for anything like 2 to 4 dimensions. And also something that is near and dear to my heart that I've studied a bit is hierarchical couplings. In particular, the masses of the quarks in the Standard Model differ from one another by a factor of 10 to the 6, and in the field theories, these are coming in the form of power couplings. And like I said, it's beautiful to me that these are the necessary things that we see in our world that we need any kind of unifying theory to reproduce. But when you consider string theory, they emerge naturally. And so the big question that lots of people in this room and myself are really interested in and have worked on, and many people have worked on it for a long time, is how do we find our world given string theory and all of the collisions that we all know about. So one bad strategy that some people do is some people might just say, all right, well, there's this huge number of vacua, let's give up, I'm done, I don't want to, it's just too hard to address this question of finding a world in this vast landscape. Two strategies I think are a little bit better. Sometimes people like to focus on, if we get a better understanding of string theory and new effects that play a role, as time goes on, we learn more and more, and it tells us more and more about the vacua and how they might look realistic. And another strategy is that we know a lot about string theory already. Why don't we just go and look at the possible vacua that we know some things about and see if it looks like. So this picture I have here is the Earth as seen from Mars. This is from a Mars rover called the Spirit. This picture was the first picture of Earth taken from another planet, actually. And if you zoom in closely, different resolutions of this image, you can see a little tiny white dot here, and that's our world as seen from Mars. And to those of us who have studied this problem, this feels a lot like what it's like to look for realistic string vacua in the landscape. So you might ask, what are some of the obstructions to studying the landscape? We heard in a beautiful talk yesterday that 10 to the 1,000 is the number of vacua. The result of Rousseau and Polchinski that is commonly quoted is that when you consider type 2B flux compactifications and you turn on various fluxes for complex structure moduli stabilization, 10 to the 500 vacua is the number that many of us know. And so the number of vacua is a huge obstruction to studying the landscape. But what I'm going to tell you about today is that the computability issues analogous to Hilbert's 10th problem that show up in the landscape really give us an issue with sort of computing broadly across the landscape and finding our world. So the outline of my talk is as follows. Something that I have studied a good deal in my PhD is called V-brane instantons. And these things are very important for low energy particle physics, as I will tell you about. So I'll review those a little bit, and I will cast the systematic study of those effects into language and computability theory.
So what does it mean, number of vacua? What does it measure?
The number of vacua. So when people talk about a moduli space in string theory and they say, take into account all the non-perturbative effects and things like that, you're generating a potential. And so the notion of a vacuum is that our world is some local minimum in that potential. And so when you compute all of these effects and compute the local minima, they're counting the number of and so I will address issues of generic computability as well, and then I'll conclude, and I will try to do this all in the next 16 minutes. So a lightning review of the Euclidean P3 instanton effects in type 2B string theory. Well, in type 2B, we take a Calabi-Yau threefold X. There's a holomorphic involution on it, which I call sigma, and there's objects that live at the divisors that are pointwise fixed called O7 planes. For consistency of the string theory, this corresponds to canceling Riemann flux of the internal dimensions. There's something called a tadpole cancellation condition, and this means that you have to introduce D7 branes to have a consistent theory in the presence of those 7 branes. So you have D7 branes wrapping divisors D in your Calabi-Yau equals X. They also are space-time filling, and these are the sorts of things that give rise to the gauge theories that give examples of particle physics in these models. Typically, a D7 brane is going to have gauge symmetry UN in which we probably type 2B. And moreover, where 2 divisors intersect that the D7 branes wrap, at the intersection you can have matter localized where D71 intersects D72, 2 divisors in your Calabi-Yau equals. So D3 instantons, on the other hand, also wrap divisors D in the Calabi-Yau, but they actually do not fill space-time. They're point-like in space-time. And one of the beautiful things about these effects is that they generate superpotential corrections. So 2 important examples of these. Historically, early on, I forget when the paper came, but the KKLT scenario, which is one of the papers that studied the emergence of de Sitter vacuum and string theory, uses such a correction in Euclidean D3 to generate a correction that can be used for K-Law modulus stabilization in the theory. More recently, in 2006, Miriam and collaborators and 1 or 2 other papers elucidated how you can have these effects that generate charged matter coupling and not just uncharged matter coupling as you see in KKLT. In particular, this is important because you can get particular Yukawa couplings that are necessary to have realistic point masses of that nature, as well as Majorana and neutrino masses so that you can have realistic neutrino masses. So the structure of the superpotential correction, if any, is determined by a spectrum of 0 modes. So in type 2B, there are 2 types of 0 modes that you want to consider. There's charged 0 modes that are D3, D7 strings, and there's neutral 0 modes, which are Euclidean D3, Euclidean D3 strings. These are the modes that are useful for generating charged superpotential corrections, and these are the modes that are common to all of these instantons. So in the CFT formalism, particularly in type 2A, a lot of work has been done in the context of toroidal orbital folds, where these CFT 0 modes are described as vertex operators, and this is very powerful when you can apply this technique. But unfortunately, as we all know, CFT is only applicable at certain areas in the landscape where you have flat backgrounds. So alternatively, these modes are counted by sheaf cohomology, and if C is the curve of the intersection of 2 D7 branes, half the canonical bundle tensored with L, which is some abelian flux dependent line bundle, counts the number of charged modes, and like I said, this is at the intersection of 2 D7 branes, whereas the structure sheaf cohomology on the instanton divisor D is the thing that counts the uncharged nodes. And for those of you familiar with Witten's beautiful non-perturbative string theory paper, where he compactified M theory to 3 dimensions, this is very analogous to his M5 analysis. So the conditions that are necessary for a superpotential correction, given a Euclidean D3 on a divisor D, where I write it in terms of the basis of divisors DI, like so, you might ask, what are the conditions necessary for an instanton to correct the superpotential? In particular, it's that the H0 of the structure sheaf is 1, and that the rest of the cohomology is 0 for all I greater than 0, which of course requires that the homomorphic genus also be 1. And so what you see here is that when you compute this as an index theorem, when you compute the homomorphic genus in this way, in the integral of the Todd class, generically you're going to get a Diophantine equation in the coefficients DI that specify the divisor. So the physical problem that you might ask about is what are all instanton corrections to the superpotential? I've hopefully convinced you that these are important for low energy physics, in particular for masses of particles and for stabilizing the moduli in these theories. This is ultimately a question about 0 modes. So a couple of strategies for solution of this problem of finding all instanton corrections given these conditions on superpotential, on the cohomology necessary for a superpotential contribution. One would be to try all possible sets of integers di. They're just integers, and you can go around and try them all, starting at the origin and having some clever path. And then you can check the conditions explicitly for each divisor and say, does it satisfy them or does it not? This is fine, but it takes infinite time, which for those of us that are trying to find the real world here is a real issue. Another alternative would be to compute the structure sheaf cohomology directly as a function of the di. This can be done in certain cases. Benjamin has a paper where he does this for instant constant F theory. And the upshot of it is that it amounts to counting points in DI-dependent polyhedra. And the point is that closed form solutions only exist in simple cases, and that generically this is a problem that we can't address. The other alternative would be to compute the arithmetic genus directly as a function of the DI, and then ask what are all DI that are going to satisfy this condition. And my point is that this gives rise to Diophantine equations. So what are the difficulties of Diophantine equations? Well, for some Calabi-Yau threefolds, the holomorphic genus is simple. So if you take the quintic and you take the hyperplane class in P4 and write the divisor as n times h with n integer, the holomorphic genus on the Calabi-Yau threefold hypersurface on the divisor there is given by this equation, which you can simply show is never going to be equal to 1. So there are no Euclidean D3 corrections for type 2 classification on the quintic. So that is a simple case, and it basically the things that make this simple is that there's one variable and they all have the same sign. But for most Calabi-Yau threefolds, we just are not so lucky. If you take a Calabi-Yau elliptic vibration over dp2, the arithmetic genus looks something like this. Notice there are many more variables, there are many more terms, and the signs are alternating, and this is the thing where we are asking what are all sets of DI such that this is equal to 1. And I don't know how to solve that, and if you do, please let me know afterwards. I would be very interested to hear that. But aside from the fact that this particular equation is difficult to find all solutions to, we all know that there are many Calabi-Yau threefolds. In particular, the largest class I know is that there are 473,800,776 reflective polyhedra, each of which is a 4D toric variety that can contain a Calabi-Yau threefold hypersurface. This was the work of Kreitzer and Skark, and it's a nice work, and they have this database online if you want to go through all of them one by one. We know that at least 30,000 of them are distinct at the level of Hodge pairs, H11 and H21, and the point is that determining all of the Euclidean D3 corrections in each vacuum across this landscape, presumably there are many more than this, but there are at least this many, requires finding all solutions to a large class of Diophantine equations. But, and this is where some of you might be familiar with the story, we know that finding even a single solution to a large class of Diophantine equations is difficult, let alone trying to find all solutions like my physical question was dictating. So, Hilbert's 10th problem, Hilbert in his long list of problems, his 10th one was basically where he was interested in these Diophantine equations and gave us a challenge, and the challenge was to construct an algorithm which, given an absolutely arbitrary Diophantine equation, can determine in finite time whether or not it has a solution. The answer that was people came to over the course of many years, and finally the last nail in the coffin was by Maria Savich in 1970, that no such algorithm can exist. So that is not good from the point of view of computing these instant-time corrections across the landscape. Even if we can't even compute one correction for each one across the landscape, let alone one to find them all. So the natural question is, do other physical effects have similar computability issues in the landscape? These Diophantine equations were very generic in the study of instant-time corrections. Those of you that are algebraic geometers know that index formulas oftentimes are giving rise to equations like this, and that it's not far-fetched that you would see equations like that show up in many places. Being a little bit more precise, and this is sort of the story of generic computability, we started being interested in this question about instant-time corrections, but then we realized, oh my gosh, this applies much more broadly. So a couple of definitions is that a set x0 is recursively enumerable if there exists some algorithm that, given x in a bigger set x, halts if and only if x is in x0. So if it's in x0, it's going to halt your algorithm, and if it isn't, well, it might not. So this is a problem from the point of view of computability because, again, you have an algorithm that might never halt, and so from the point of view of trying to find our world, infinite time is bad. So the thing that we really want is that set x0 is recursive if there exists some algorithm that, given x in x, determines in finite time whether x is in x0. So essentially, this is a finite time classification algorithm. I have some physical property that I want to ask of each vacuum. I want to say, is it true or is it not true? And in finite time, I have an algorithm, if it's recursive, that can tell me whether it is in or out of the set. And this is exactly what we want for computation. So in this language, the solution to Hilbert's 10th problem, i.e. that there is no solution, is the statement that S is non-recursive in D, where D is the set of all Diophantine equations, and S is the set of Diophantines with solution. The set of Diophantines with solution certainly is recursively enumerable, because if you just file solutions, if it has one, you're eventually going to find it, but you might never find one. And Marius-Davich's theorem is basically that S is non-recursive. So, casting the physical problems in a little bit more broad context, if you take a physical property P, any property for the time being, which defines a recursively enumerable set, that is, I have some question that I want to ask of my string vacuum, the answer is either yes or no. A physical property P that is recursively enumerable is one that defines a recursively enumerable set. So what you want to know is it true of a string vacuum? So one particular example of what P might be, and this is related to what I was just asking, instead of all, you might think, is there a Euclidean E3 instanton correction with superpotential? And then for each vacuum, you could go through and apply the conditions and say, yes, there is, yes, there is, or no, there is not. But any P that defines a recursively enumerable set is good for this purpose. What is important here is that there is also a theorem improving the negative solution to Hilbert's 10th problem. Marius-Davich also showed that any recursively enumerable set is Diophantine. So recursively enumerable sets are the ones that correspond to physical properties that we're interested in, and the fact that each one becomes a Diophantine set means that P is true for X if and only if there is some Diophantine equation dP comma X that has a solution, where dP comma X is a particular Diophantine equation in this set, large D P comma X, which is roughly the set of Diophantines coming from string theory, corresponding to a physical property P and a vacuum X. So ultimately what we're asking about when we talk about computability in the landscape is asking about the structure of these Diophantine equations with solution coming from a physical property P and a vacuum X in the set of all such Diophantine equations. So like I argued earlier, there's an enormous number of vacua in particular, and there's also many properties P that you might think up that are relevant to calculate for relativity physics. And so ultimately this implies that there are an enormous number of Diophantine equations coming from string theory. So in particular, SP comma X is a set in the set of all Diophantine equations with solutions, and because the landscape is large and there are many physical properties that you might consider, this set here has many elements. So in particular, if you could amazingly prove, which is a challenge to all of you, that SP comma X is in fact this set S, then Hilbert's 10th problem would apply directly, and we would have this computability issue. That is a hard proof to do. We did not, that is for future work. We did not attempt that in this paper. But given that this set is so large in the set of Diophantines with solution, the computability conjecture that we put forth in this paper is that SP comma X is non-recursive indeed, the set of Diophantine equations. All right, no questions. So, needless to say, this is basically borrowing a result from Hilbert's 10th problem and using it to say something interesting about the landscape. That is, recursively enumerable sets are Diophantine by a theorem, and therefore properties that you might be interested in string theory can be encoded in a Diophantine equation. And given the large number of properties in vacua, you have computability issues in the same way that you have computability issues in generic Diophantines in the Hilbert's 10th problem. So, like I said, we were initially motivated by a systematic study of non-perturbative superpotential corrections, but this is actually much broader than that. So, two comments are, if our conjecture is true, then there's no algorithmic way of computing non-perturbative effects across the entire landscape. That is, you might be able to do it patch by patch, but the point of the negative solution to Hilbert's 10th problem is that there is no way of having an algorithm that would do it across the entire set of Diophantines. So really the question is, how big is the set of Diophantines coming from string theory in the set of all Diophantines? So the landscape in that case is in particular patchy. So what I would say is see our paper for example of patchiness. We're really ultimately interested in instantons in addition to this computability issue. And so what we showed there is that if you have a Calabi-Yau threefold elliptic vibration with a single section and some other assumptions about your type 2D compactification, you can find all uncharged corrections to the superpotential. And the if not, which is what we all hope, is that some beautiful aspect of string theory causes it to yield diaphantenes for which there exists a solution out of it. That is a very hard thing to study, but that is the hope, and it would be beautiful. So please show it. So thank you. That's all I have to say.
Do you have really sufficient and necessary condition to tell if an instanton contribute to the superpotential or not?
Is there an if and only if?
Yes.
Yes. So I mentioned it on a slide. Ultimately, the sigma action on the Calabi-Yau induces an action on the bundle. So you have Z2 equivariant cohomology, and in particular, the conditions are so it splits H star into H plus and H minus. And so the condition is that H plus is equal to 1 and the rest are 0. So it's a little bit more structured than what I told you, but I didn't want to get into this is not necessary for the computability discussion. That is a necessary and sufficient condition. There's also a subtlety if you turn on certain fluxes in your model that some of the zero modes might be lifted, but in the absence of flux, this being 1 and the rest being 0 is the condition.
Because for M5 instanton, I think Witten's condition is necessary but not sufficient.
It is.
You could have other anomalies, just looking at one anomaly.
It's necessary but not sufficient. In particular, his when you say Witten's condition, do you mean his index condition or
the
arithmetic?
arithmetic.
Yeah. So in particular, the arithmetic genus constraint is just an index. I mean, you could have in higher cohomology.
So for the instanton, you have necessarily insufficient condition. Because if you don't, I don't understand.
A Witten's condition is a necessary and a sufficient, but they're not the same. The sufficient is the Hodge number, the 1, 0, 0, 0.
Okay.
Right. And so that's effectively what I'm saying in this context. So Benjamin, who's sitting next to you, actually has a paper where he discusses the uplift of these types of instances to F theory, where they interpret them as M5 instances may not cohomology accordingly.